Yeah, we can.
Okay, so let's get started then. So once again, we're going to do review for chapter 7 today. So Monday, you're going to have your exam, and then so Monday's SI session will be after the exam. So we're just going to move on to the next chapter. So with chapter 7, I have questions 1 and 2 today are regarding electron affinity and ionization energy. I think it was the last thing yesterday. And I didn't get to these questions. I just want to go over them briefly. And then we're going to review wavelength energy, frequency, that kind of stuff, electron configuration and quantum numbers. And I think that's all I have for today. If you can think of something as we're going that I forgot, feel free to let me know. Let's see, anything else? I think that's about it. Are there any questions or comments before we start today?
Can we do formulas?
Yes, good question, Ben. So let's do some formulas. I almost forgot. So who can think of some formulas for chapter 7?
C equals wavelength B.
Okay, I didn't see who said that, but someone said C equals wavelength V. Yep, so this is C equals, a wavelength is this lambda symbol. So we use that with light waves. So C is the speed of light, and this is 3.00 times 10 to the 8th meters per second. Lambda is I forget how you spell lambda. I think it's something like that, lambda. That's the weird looking upside down Y. And this is measured in meters. And then V, this is frequency, not velocity. Remember that, the velocity is the speed of light. And the frequency is in hertz, or sometimes seconds to the -1 power. Another equation you can use with light is the energy of a photon is equal to Planck's constant times the frequency. And then another one would be the energy is equal to Planck's constant times speed of light divided by wavelength. So let's just type out what these are here. So E, this is energy of a photon measured in joules. H, this is Planck's constant measured in, or this is just a value. This is 6.626 times 10 to the -34 joules times seconds. So the speed of light and the Planck's constant, those are always going to be the same. So you don't ever need to change those. Let's see, there's one other equation I can think of. Oh no, there's two other ones. So one of them here is, let's see where it is. So change in energy is -2.178 times 10 to the -18 times 1 over n final squared minus 1 over n initial squared. So this was the one where we used the orbital levels. And so you were saying if you had an electron that moved from one n level to another one, then this would be the energy change associated with that. And so the delta E change in energy from moving an electron energy levels, and this is measured in joules. And then the N's, these are just like 1, 2, 3, 4, ... These are the energy levels. So if you're given a problem like this, it's literally going to say like, you know, an electron moves from level n equals 1 to level n equals 3. So, and then you just kind of plug it in there and put it in your calculator. So does anyone remember this keyword ground state? I'll just type it. Does anyone remember what ground state means?
It's the lowest level.
Yeah, so what number does that represent, Dylan?
I think it's 1.
Yes, very good. So for ground state, n equals 1. Okay, and then I can think of one more equation, and that would be the one for de Broglie's equation. Let me just, so I don't mess up the equation here. I believe that is, got it here, hold on.
In the homework for the change in energy,
Yep.
instead of in the brackets, they just had z squared over n squared. Is that like the same thing?
For this whole piece here,
Yeah.
Kristen? What is the z? I didn't know. Do you remember what that is?
I can't, I don't remember, but like it was for a hydrogen atom, and for the z, for you just plugged in 1 every time.
Oh, so it was like z squared up here?
Yeah, z squared over n squared.
Yeah. So good point. For different atoms, you'll be doing different like z's up on the top. But for this class, they're always going to give you a hydrogen atom. At least they always have in the past. And for a hydrogen, the top is just 1. So it should look like this. Usually in the problem, it's going to say, what is the energy change for a hydrogen atom? I don't think they would ever give you anything else. Does that make sense, Kristen, or have you seen something different?
It does, thank you.
Okay. So I found this last equation I was looking for, and this was the de Broglie wavelength. And this is h divided by mu is wavelength. And so lambda, this is wavelength. H, this is Planck's constant again. And I wrote that above. M, this is the mass, and you have to measure this in kilograms, not grams. And then U, this is velocity, meters per second. So the de Broglie wavelength, this green one here, is specifically for if you have an object that has mass. So photons do not have mass, so you can't use the green equation. But if you have an object that's traveling so fast, it starts to exhibit a wave behavior. And so there you can calculate the wavelength of that massive object that's traveling. So these are the equations I can think of. Am I missing any, or what questions do you have on the equations for chapter 7? So a couple questions. So Z is atomic number. Okay, so I guess the Z on top here is atomic number. If you had to put here, so hydrogen would be 1. Honestly, I've never done anything other than the hydrogen. And then why is more than just E with Z, E, F, F? There's more than, I guess I don't understand the question here. There's one more that is just E with Z, F, F. Okay. Maybe if you could rephrase your question. I didn't quite understand what you're saying there, but. All right, so let's start doing number 1 and 2 here. Now, number 1, I'm looking for the equations showing the electron affinities, and number 2, I'm looking for the equations showing ionization energy. So can anyone tell me what, if they were here yesterday, what does electron affinity mean?
That's like the energy associated with like giving away an electron, basically.
Yes, actually, I can't remember if it's giving away or taking. Add it, yeah. So electron affinity, you're adding an electron. Thank you, Elizabeth. Obviously, I don't have to take the exam, so I don't have to have this memorized. So yeah, electron affinity, we're adding an electron. So what I want to see here is if you were going to write an equation for the electron affinity, you take whatever your metal is or whatever your atom is, and it has to be in a gaseous state. And we are going to add an electron. So we're going to add an electron. And what is this going to become? So this will become Mg minus as gas. And this has to be done when they're in gaseous state. So this here, this would be the equation for the first ionization energy. So now that you see the form, we're just adding an electron and changing the charge. Try to do the second and third one. So in this case, we'd be starting with Mg minus. And for number 7, I want you to do the ionization energy. So this is just the opposite. Rather than adding an electron, we're going to be taking one away. So we started with magnesium gas, and we are going to be stripping one off of the magnesium. So this would go to magnesium plus as a gas, and one of the electrons would be removed. So why don't you spend just a minute or two and try to see if you can just follow the same format here and get the second and third equations for each of these. And let me know what questions you have as you're working. Okay, so looking at the electron affinities, so for the second equation, we're going to start off as a -1 charge. And again, we have a gaseous, and we're going to remove another, or no, add another electron. And if we add an electron, that's going to go into the magnesium as a charge, so -2. And then for the third one, so once again, we're starting with a 2- charge here. starting where we left off at the last one, and we're adding another electron. And then this is going to go to Mg3 minus gas. So pretty simple. All right, so number 2 then, so the ionization energy is the opposite. So the first one, we took off one electron and got Mg plus. So we're going to start here with Mg plus, and that's going to, I got a chat here. So Francis asked, does it matter what side the number, we put the negative side on? Are you talking about the electrons, Francis? Like 2 minus, oh, okay, good question. So the question was, can I write Mg, for example, right here, can you write Mg 2 minus or Mg 2 minus like that? To be honest with you, I do both, and I think a lot of people do both. I've really never thought about which one's correct. If somebody knows that there's a correct one, they can tell me, but I've never seen anyone take off any points for that. That's a good question though. So lastly, we start with the Mg2 plus gas, and this goes to Mg plus 3 gas. So again, you can do 3 plus or plus 3. Yeah, I'm not sure which one it is, but I've seen both. So what questions do you have on the electron affinity or ionization energy equations? All right, so let's work on some review then. So let's apply these equations we were talking about and try to work through numbers 3, 4, and 5. And let me know what questions you have as you're working. All right, let's begin taking a look at these. I know a lot of people are still working, so feel free to keep going as we begin our discussion. So number 3, does anyone have any opinions or want to take a shot at number 3?
Use C equals lambda V.
Okay, yes. So the first one, we want to use C equals lambda V for number 4. On number 3, so we don't forget this one. This one I mentioned here. So the top one here, this one is going to have the longest wavelength. The bottom one is going to have the highest frequency. And remember, higher frequency also means a higher energy. So the bottom one also has higher energy. And then regarding the speed, so be careful with this one. This is the same speed for both. So these are both going to be traveling at the speed of light. So it doesn't matter the wavelength or the frequency. So number 4, we are looking for the frequency and we're given a wavelength. So the relation between that is C equals lambda V. So reorganizing this to solve for frequency, we get C divided by wavelength. And so we're just going to put in our values. So C is 3.00 times 10 to the 8th meters per second. And then the lambda is 2.9 meters. So this is going to give us 1.034 times 10 to the 8th hertz. So that's scientific notation. And if we want to translate it to megahertz, then we have to do a little conversion here. So there are 1 times 10 to the 6 hertz in 1 megahertz. So you're just dividing the number by 1 million and you get 1.034 megahertz. All right, and then looking at number 5. So number 5, we have a wavelength as given as 625 nanometers, and it wants to know what is energy. So there's 2 ways to do this. The easiest way is going to be using the equation E equals hc over lambda. But you can, if you want to use this equation, and then also use the equation with frequency, you can do that as well. You're going to get the same answer. So putting in C, we have 6.626 times 10 to the minus 34, 10 to the 2. Oh yeah, thank you. That is a little typo here. So it should be 103.4. Thank you very much. All right, so back down to number 5. So 6.626 times 10 to the minus 34 times the speed of light, 3.00 times 10 to the 8th. And then we're dividing by the wavelength, so 625 nanometers. Now, you cannot just put 625 in here. You have to change it to regular meters. Now, the easiest way to do that is just do times 10 to the minus 9. So when I write times 10 to the minus 9 here, that's because a nanometer is equal to 1 times 10 to the minus 9 meters. So you can do your conversion separately if you want, but it's easiest if you just add the times 10 to the minus 9 right on the end. So just putting that in your calculator, I get that the energy of 1 photon is 3.18 times 10 to the minus 19 joules. what questions do you have on questions 3, 4, and 5? All right. So in that case, if you don't get this, I'll post the answer key as well, along with the other worksheets. So let's, why don't we do numbers 6 and 7, and I'll try to leave this other stuff up here. So as you're working, feel free to ask any questions you have on these, or if you have any other general questions about anything in this chapter, I'd be happy to answer those for you as well. Okay, let's begin on number 6. So in number 6, we're looking for the full electron configuration and the shorthand configuration. Also, if you didn't check in or put your IOC email in the chat, I would appreciate if you do that so I can record attendance. So let's grab the full configuration first. So you're going to need a periodic table, and I like to use this one and try to like superimpose this in my mind on top. So oxygen is right over here, box number 8. So then if I was going to superimpose that onto this one, this would be located right over here. So we're in the 2p and the 1, 2, 3, 4th box in the 2p. So let's begin writing our configuration. So we have 1s with 2 electrons, 2s with 2 electrons, and 2p with 4 electrons. So that would be our full configuration. And then the shorthand configuration, or the noble gas one. So we are going to put in a square bracket the most recent noble gas. So the way you find that is you're just looking at like the most, the one you passed. So if we were going to get to oxygen, we come across here, we get to helium, then we come down to the second row, which we're still going, and then we get to oxygen. So the most recent one we passed would be helium. So in this box, we're going to put helium and then start at the next row. So that would be 2s2, 2p4. All right, so now on chromium. So once again, chromium is located right here, box number 24. And that would be right here on the periodic table blocks. So right here, the 4th one in the 3D. So let's write out the full configuration first. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now, who can tell me for the chromium what is wrong about this configuration?
4s1, 3d5.
Very good. Yes, that was quick, Ben. So, oh, stop sharing. So the rule is, we discussed this yesterday. Let me write it down. No D4s and no D9s. So over here, notice we have a D4. So this part we're going to cross off. And this is going to take one of the electrons from the 4s. So this is going to become 4s1, 3d5. Very, very common trick question. So then getting the shorthand configuration, we have a square brackets, and the most recent noble gas was argon. And so this would be 4s1, 3d5. What questions do you have on the electron configurations? Okay, so let's do some quantum numbers then. So I also wanted the box diagrams. Now, if you can get the quantum numbers without drawing a box diagram, you're like a pro. But for me, I always usually have to draw the boxes. So for oxygen, let's start drawing out the boxes. So we're just going to follow this notation up here. So we have the 1s box, then the 2s box, and then the 2p box. So the s orbitals always have 1 box, the p have 3, the d have 5, and then the F has 7. I don't think you're ever going to get an F. So next thing we want to do is figure out the number of electrons for oxygen. So this one's oxygen. And from the periodic table, oxygen has 8 electrons. Another way you can get this is you can add up the exponents here on the 1s2, 2s2 thing. So we have 2, 4, 8. We have 8 electrons. So let's add those in as arrows. So 1, 2, 3, 4, 5, 6, 7, 8. So let's just circle the last electron we drew here. So this one was the last one right here. So the last electron is the one we care about for doing quantum numbers. Now technically our box diagram is done. You don't really need to circle the last electron, but I find it useful when we're doing quantum numbers. So next thing I want to do is number the boxes. So for the P, the last electron is in the 2p, so let's number the boxes for this one. So the middle box is always 0, the right box is +1, and then going to the left is -1. So we're counting out as we go. And now that we have our box set up, we can start thinking about getting our quantum numbers. So that would be NL, ML, and MS. So who remembers how we get the N quantum number?
Whatever, like, I guess, like, if it's 2s, it'd be 2.
Okay, yep, you got it, Ben. So it's this coefficient right here. So this is 2, so the N is 2 for quantum number. For the P, or for L, this is determined by the letter here. So let me write this out. So the S block, the L is equal to 0. For the P block, the L is equal to 1. For the D block, L is equal to 2. And then the F block, it's equal to 3. So because we are in the 2p, the L has to be 1. And that's just a rule. It's always based on the letter. Who remembers how to find the ML quantum number?
Isn't it like negative L to like the positive L? So like in this case, it'd be -1 to 1.
Very good. Yeah. So it's that's the like span. It has to be one of the numbers between -1, 0, and +1. So when you're asked for a quantum number, you're supposed to choose which of those it is. And so in this case, it would be -1 because the last arrow we drew here is in the -1 room number. So ML is equal to -1. So the box number of the last electron. And then finally, the MS quantum number, this is -1/2. So an up arrow is +1/2, and a down arrow is -1/2. So our last arrow we drew is down, so that would be a minus. What questions do you have on the orbital box diagrams or the quantum numbers?
Gotta go, Matt. Love you. Bye.
Okay, see you, Ben. So I will leave up number 7, and I have 2 more questions on today's review, both of which are really common multiple choice questions. The first one is asked about excited states. So number 8 is excited states, and number 9 is which quantum number sets are allowed and which ones aren't. So let me just give you a quick review on excited states. If you already know, then feel free to start working. So what you want to look for in an excited state is which one of these is the correct electron configurations. And if it's the correct configuration that it should be, then it's a ground state. But if something is off, if something is different than normal, then that was what's called an excited state. So just look for some differences in what it is and what it should be. And we'll take about 3 minutes or so to look at these, and then we'll wrap up for today. Okay, let's look at 8 and 9. I know I didn't give you much time, but I want to make sure I get you out by 5. So here's how I look at this. This looks a little weird because this should be 2s2, 2p4. But in this case, the 1, there's only 1 electron in the s. So this means it's excited, which means one of the electrons moved from the 2s up to the 2,5, or the 2p. So this one is an excited state. It's different than what it should be. Looking at the next one, we have 5s2, 4d10, 5p1. That's the correct sequence. So this one is ground state. For C, we have 4s2, 3d10, 4p5. Once again, that's the correct sequence. Nothing looks off there. So this one's ground. And then this one, we have 5s1 and then 4d10. So this should be 5s2, 4d10. But one of these electrons is moved up into the 5p. So since it's different than what it should be, this one we know is excited. Okay, so let's look at lastly's A, B, C, and D. Now, I don't know the best way to go about this one, so why don't I give you the answers and we'll explain why There's 2 that aren't okay. So these are the answers. The first and last are okay, and the middle ones aren't. So these ones I think are just kind of recognition after doing a few examples. So why is B incorrect? Well, B is saying, so the L is 2. That means we're in the D block. Or in other words, the rooms have to be, the rooms have to be 0, -1, -2 to 0, +1, +2. So the L is the range of the rooms. However, here in the middle, it's saying our room number, ML, is 3. Well, 3 is not one of the possible rooms for this configuration. Therefore, we know this quantum number set is incorrect. So for part C, same kind of thing. So L equals 1. We know that the room numbers have to range from -1, 0, +1. And once again, it's telling us our room number here is -2. And that doesn't make sense because that's not one of the available rooms. So that's kind of what I look for when I'm looking for quantum number sets like that. I just kind of draw out the rooms. All right, I know I went over a couple minutes, but if you have any questions, feel free to stick around. I can help you out with that. Otherwise, I'll try to post the answer keys for these and everything on chapter 6 in about an hour or so. So otherwise, we'll see you guys on Monday, and good luck on your exam. So I just saw your message, Gracelyn. And that's just how you're Sachin. So 8A, why is it not ground state in the last worksheet labeled as normal 3B, 8A? So this one here, so I think what you're asking, Gracelyn, is why, why is the 2 and the 4 rule where it like moves 1 electron up? So remember, this only applies when it's D. It doesn't apply to the P. So if it was like, for example, if it was 2s1, I don't know how you would have this. Like, let's say it was 4s1, 3d5. This is ground state. This is okay. This is ground. Because the D5 rule applies. But in this case, this is a P. So the P does not have the D4, D9 rule. Is that what you were asking, Gracelyn? Okay, yeah, good luck. So Sachin, you asked 8D. I thought the D orbital took the electrons from the 5s. Yes. Yes, Sachin, this is the correct case if, so this one, if you had, for example, 5s1, 4d10. So this one would be ground state. However, this is not the configuration that was given. We have another electron here. So the question is, if you were going to add 1 electron to this configuration, where should it go? Well, it should go right in here, right? It should be put in the S. So this should be a 2 to fill in the lower energy levels first. However, it was put in the P. And because it was put in a higher level, that means it's excited. Does that make any sense or not really? Okay, great. Good luck. Do you have any
Thank you.
questions, Megan?
No, I'm good. Thanks.
Okay, good luck.